Hello and welcome to Dataless You. I'm Paul, coming to you from Brooklyn. Today we are going to take a look at finding the volume of rotated solids. This is a major concept in calculus, particularly in integration calculus. We're going to do a specific problem from a favorite textbook of ours, James Stewart's Single Variable Calculus, Concepts and Contexts, version 3. Open up to page 457. We're going to look at number 5. Pretty much a classic question. We have a few equations given. Y equals x cubed, classic cubic, and y equals x, an even more classic equation. We're only going to be concerned with the domain of all x is greater than or equal to 0. So let's take a look at the shape in question. Basically, we're really only concerned with what happens between 1 in x direction and 1 in the y direction. Because as we know, the line y equals x looks like so, arriving here to this point 1, 1. And the cubic equation, which curls up from down here, but we're not concerned with it from there, and then at the origin, it goes through the origin, and then curls up like this, and it meets y equals x right there. So we're concerned with this region here, bound by these two curves. Okay, y equals x on top, and below y equals x cubed. Now, to make this a solid, we have to actually rotate it about the x-axis. Okay, so imagine spinning this around in a full circle. And so you'd first get your mirror image down here. And if you imagine the solid that would make, again by spinning this around the x-axis, rotating it in other words, that's the solid for which we want to find the volume. The question is, what is the volume of this solid? And to do so, we have to do just a little bit of nifty calculus. The most important thing that you want to see is that the shape created is a circle, probably a more perfect circle than that one. And the outer radius, right, this circle, is created by the line y equals x. And the inner radius, this one that's going to be created between these circles, is called y equals x cubed, or is described by y equals x cubed. Now, to find the volume of the solid, we use what is called the washer method. Because if you take a closer look at those circles, it looks like a little washer. So we're going to take the integration from 0 to 1, so that's in the x direction, from 0 to 1, essentially of just two circles. So I'm just going to start by saying pi r squared minus pi r squared. Of course, they're different r's. Right, so this larger circle minus this little circle gives us at first the area of this single washer. Maybe it's this one right here. Right? Oh, get out of there. Right in here. Right, that's the washer. But of course this is calculus, so we're going to do this infinitely along the curve from 0 to 1. And so our change in x, which is the width of the washer, is dx. So essentially an infinitesimal an infinitely small width, and we will sum, an integral is a way of summing up this area, all of these areas. So notice we can just quickly factor the pi out, and at this point we're just doing some integration. And instead of writing r, I'm going to write what makes that r, which of course is that curve y equals x. So we're talking about x for the r squared. I factored the pi out from both of them. And of course, you can factor constants out in front of integrals, one of the nice parts of integrals. And the inner radius is that other curve, and that's x to the third, which we have to square. And all of this, of course, times that infinitesimal dx, which we need to take the integral. This equals, we still have pi. We're going to have it times, though, the integration now. X squared integrated, of course, is x to the third over 3 minus, well, we skipped a step. This equals x to the sixth, which then, when we integrate, is x to the seventh over 7. Right, we're going to evaluate that integral from 0 to 1. Okay. We can plug in 1 easy enough, and we see we get 1/3. We still have our pi out front, and we plug 1 and we get 1/3. Right? Minus, when we plug 1 into x to the 7th over 7, we get 1/7. And of course this is all minus 0, because when we plug 0 in there, we just get a big fat 0. This would of course be bracketed with the pi still waiting for us out front. In integration, you will notice, I always have to stress this point with my students, that there's a fair bit of tedious fraction work to be done. Our common denominator there for 1/3 and 1/7 is 21. So our final answer, after doing just a touch of fraction work, is 4 pi over 21. Which is indeed the volume, we'll put that back here, of the solid generated by rotating the area bounded by the curves y equals x and y equals x cubed around the x-axis. I hope you've enjoyed this video, and I will see you in the future.